We're all set? Yep. Okay. Okay, welcome to our weather discussion for today. I'll do the first part. I've got a little bit about the current weather and then a little bit of discussion about what was interesting about our recent slushy, snowy, freezing rain mix. So that's what I'll talk about today. And then Patrick is a recent award winner of a campus-wide Natural Sciences TA award. And I don't know if I announced that last week, but if I didn't, I'm sorry I didn't. But I won't do it again either. But congratulations. I don't want to tell you that every week. I had a thought that I might have said it last week. It doesn't come easy. And Patrick will give the discussion, and you'll realize right away if you don't already know why he's a worthy recipient. So two things. First, current weather, and then a little bit of a discussion about aspects of the recent snow and slush event. So current weather first. Here is the infrared satellite movie over the last 6 hours. And most of the exciting weather in the eastern two-thirds of the country is now abated and moved offshore, and some of it is showing up as a really nice swirly here south of Greenland, another one just off the coast of Nova Scotia. So there's a couple of different disturbances there that are not so well defined as we've seen in prior times this year. But overall, in the central United States, we're the beneficiary of a tropical flow from the eastern part of the Pacific Ocean. It comes all the way across Mexico and into the middle Atlantic states. It was 80 degrees in Washington, D.C. Yesterday, something in the 60s in Philadelphia. Lots of really warm temperatures. They're probably going to change in the near future, but still incredibly warm. And then today, there's some pretty heavy precipitation in the south central part of the Mississippi Valley. The main weather event across the country today is this extraordinary disturbance off the coast of California. It's at the latitude of San Francisco. And just by this picture, we'll see a better one in a minute, but just by this picture, you can see this is really cold air aloft. Open cellular convection everywhere on the backside of this counterclockwise circulation, and extremely heavy snows in the Sierra and parts of the Cascades. They had 10 inches of snow in Portland, Oregon yesterday. And then this thing creeped slowly down along the coast. Offshore is the key thing for major snow under these kinds of circumstances. If it's kind of right along the shore, it doesn't snow in Seattle, it doesn't snow in Portland. But offshore it can. And really extreme snows in the Sierra. Great news. It's not going to be lowland flooding, but it's going to be muddy water in the bank. So just exactly what they need. California, though it's taken some punches this winter, has experienced a substantial recovery from the drastic drought situation that it's faced over the last several years. And this is one of those elements that's helping to do that. So we'll look a little bit at that structure as well as we move forward through the discussion here. Let's see. I want to take a look at the radar as well across the continental U.S. So here it is. And you can see elements of precipitation all the way from the LA area where it snowed overnight in LA County. It was snow on the hills in Hollywood. Really interesting, doesn't happen very often. And I bet you this is fairly late in the year for that to ever happen. So although the coldest month of the year in Southern California at 850 is March, so it's about on schedule. LA has an average -5, I think, or -4 or something like that. Very cold, actually, for them. But here's the precipitation associated with that big disturbance. Much of it, you can't see the circulation is offshore. And then a little bit of precipitation over Tennessee, northern Mississippi and Alabama, and then across the central part of Arkansas. And then some lake effect in the lees of Lakes Ontario and Lake Erie. And just, I don't know what this all is, but a little bit of snow shower maybe coming across southern Iowa. So really the main story is out west this morning. And so let's take a look at the satellite imagery out there. So there's a glorious system there. Isn't that just gorgeous? And the latitude is, as I said, right about the latitude of San Francisco. You can't miss the obvious counterclockwise circulation of all these convective elements. They're caught up in a really intense upper disturbance. Poster's just telling me that the surface analysis does not really have any obvious frontal structure analyzed. Maybe that's because a large part of it's offshore, but it might just be because it's just a big cold upper low. I don't know. So I wish I had spent time thinking about that. But it's part of a larger circulation that also is intriguing. Here's the state of Hawaii. Earlier this week, maybe it was last Friday too, there was an obvious plume of moisture that had legs coming out of the tropics going right across Hawaii. They did have substantial flooding there Friday and Saturday across much of the state. And then there's another disturbance to their southwest right now that's apparently also maybe got its sights on maybe the northern islands in particular. But broadly speaking, there's a big ridge across the eastern part of the Pacific that's been there all week long, and you can see the cloud streak really clearly defining the northern edge of that part of the circulation. And then suddenly, this development of a trough out here off the west coast. And it's not sudden in the sense that it happened overnight. It's been gradually happening over a couple of days leading to today, but that's a big difference from the broad anticyclonic circulation over really from the central to the west coast, that part of the Pacific Ocean. So this is an anomalous part of that broader circulation. And then to the west, a couple of what looked like fairly intense disturbances. Frankly, time got away from me this morning. Couldn't go further west and see whether or not they actually look as ominous as they may, or are as ominous as they might look. Okay, so that's interesting. I wanted to take a look at the superpeats to get a sense of what's going on with that, with the structure of those, just the disturbance off the Pacific coast, especially. So here's where we are at 500 millibars this morning. Look at this, Pete added the days now. So I have one less way to look like a fool. I still have plenty, don't worry. I mean, I'm not going to exhaust all of the possibilities at my disposal, but at least that one may disappear over a period of time. So a couple of things about this map that are of interest to me. One of them, I'm drawn immediately to what's going on off the west coast. First of all, extraordinarily strong horizontal temperature contrast. One can't be even certain if this is exactly what it looks like because there's no observations out here, but one can imagine that there's a strong upper level front on the western side of this deep cutoff low. And that feature, it has temperatures in the minus 35 to minus 38 at well, minus 36, sorry. Minus 35-ish range at 500 millibars just off the north coast of California. That's really cold for that latitude. The water is probably 55 Fahrenheit, so what's that, 12 or so degrees C? So you got a 47 degrees Celsius temperature difference over just, 5 kilometers. So that's a lapse rate well over 8 degrees per kilometer. That's conditionally unstable and more. So all those thunderstorms are happening for free, effectively, and contributing to some of the precipitation offshore and maybe even some of it onshore. But look at this post. As you said, no baroclinicity to the eastern side here at 500 millibars. We'll have to see if it looks like that further down. But the other interesting aspect of this broad picture is how strongly deformative the flow is. There are not a lot of waves in the flow everywhere west or east of this location, except well north. So this flow across the continental U.S. is strongly stretching. It's deformative here, it's confluence here, and there's a little bit of confluence actually all the way from the central part of the country to maritime Canada. But there's no troughiness. And actually that's not different from what the early part of this week looked like. And so all these calls for 22-inch snowfalls in Minneapolis, in the absence of a really strong upper level wave, had me wondering, is this really going to be that strong of a low level of phrenogenetic event that will deliver that kind of snow? And it turns out it was not. So I want to make some comments about that later on. But broadly speaking, as we get near the beginning of March, really energetic flow over the western part of the hemisphere and pretty wavy, pretty undulatory as well. So kind of setting us up for some interesting weather over the next several days, maybe not each of those individual days, but as the days march on. Let's take a look at 850 and see whether or not there's any temperature structure at all. You get intercepted by the mountains. Impossible to really discern what's going on at 850 everywhere inland because 850 is below the surface in many of these places. But you can see a vestige of the baroclinic zone at 500 farther to the west, so one gets the idea that there's a cold dome that spreads. Let's see, if this is the coast, it spreads out like this. The further down you go, the further to the west it is, and that's sensible. So that's a pretty intense baroclinic zone that's showing up here in the analysis associated with this broad cold dome. It's minus 8 to minus 6 everywhere here at 850. So that's only 1.2 kilometers above a plus 12 degree ocean surface. So that's 18 degrees in 1.2 kilometers. It's absolutely unstable in the boundary line by a very rough calculation. So no surprise there's widespread convection there. And it gets no discouragement the higher up those convective plumes rise. And then a strong baroclinic zone. It's not 80 degrees in DC today. They had to be on this side of the plus 15 or plus 12 degree or plus 15 degree 850 isotherm. They're not now. So Michael's probably wondering what's going on, but minus 3 at near Washington Dulles this morning at 12Z. And strong cold convection across everywhere. New England, Pennsylvania, Middle Atlantic. Stays warm down over southern Florida. Okay. else would I show here? Okay, now I think I'm going to turn my attention to our recent storm, with maybe some places where I'll come back here. I'm definitely coming back to this model run. Well, I'll start with this, I guess. This is the model run from Tuesday at 12Z. And the reason I'm showing it is because this is the one of several in a row that looked like this. That there was this cyclone getting itself organized in eastern Wyoming, and with snow at the front edge of the really cold air that was spilling southward. Look at these pressures, they're well over 1030. Thickness contrast in the blue is very strong. And there's forecasted snow across the Dakotas, and that's going to inch its way towards us. And I want to show this as an old forecast just because it caught my attention while we were watching the anticipation of this storm. So by Tuesday night, the snow was inching towards Madison, spread across the southern part of Minnesota, central Wisconsin by midnight that night. And then this is really interesting, that even in this forecast and several others like it, this was for Wednesday morning. Precipitation over the southern part of our region, then some freezing rain rimming it to the north, a reflectivity gap, maybe, and then snow to the north, snow in Minnesota and the central part of the state in northern Michigan. This was a consistent theme of some of these forecasts. Notice also, no particular disturbance at sea level developing. This is 992, so they're drawn every 2 millibars at tropical. And so 990 over central Kansas is not really much to write home about, and the pressure will rise because that's kind of lee side lower pressure. So watch what happens. And then it all fills in really strong mixed precipitation, which was exceptionally well forecasted here, days in advance. I don't think anyone was surprised by the slush puppy-like texture to the stuff that was falling out of the sky, and then the Thursday morning glaze of ice. That was also forecasted. So this was an excellent forecast for us. But if you were in the Twin Cities, you were looking for 20-ish plus inches of snow. You ended up with about 8. Now, as a young person in the Twin Cities, you're used to disappointment. You follow the Twins and the Vikings. But nonetheless, it never feels good to expect a 20-inch snowfall when all you get is about 8. You know, and maybe it was glazed. Did you hear that, Patrick, about the Vikings? So that was troublesome. And it struck me, and look at the cyclone, 992, and this is because tropical's hyper in drawing its isobars. This is not a really intense low-level disturbance, right? But it's a really intense something, and that something is, watch this. Oh, I guess it's this one here. The purple shading here is frontogenesis. So this is an incredibly strong low-level frontogenetic disturbance. And so when you have this axis of intense frontogenesis, you'll have a thermally direct circulation, the warm air will rise, the cold air will sink. So the circulation right around Madison was sufficient to drive a pretty decent precipitation event. It was too far north for Minneapolis to really derive that benefit. Southern Michigan had 16 or so inches of snow, and parts around Detroit. That's close to the frontogenesis band in southern Michigan. So this was the part of the storm that actually did perform, and one could have expected it was going to perform rather like it did. Absolutely no substantial upper wave that would have given what I'll say is a double whammy for strong, heavy snow. You need to have a synoptic scale forcing that produces a cyclogenesis event. On top of that, the frontogenesis. If all you have is frontogenesis, and you're stranded to the northwest of that baroclinic zone, you get just the frontogenetic snow, and you end up, you know, waiting for the Twins to win a game in the spring because you got disappointed by the snow. So very, very interesting. Now, my suspicion was from the beginning, but I never had the guts to just say, I think there's something wrong here. But let me just show you this. We'll go back to Tuesday morning. So Tuesday morning, at the beginning of this forecast, there's something lurking off the west coast. That'll come into view on this domain in just a minute. This is disturbance number 1. That looks like, hey, maybe this is I think what the Weather Service might have been thinking was there's going to be a phasing of this wave, and maybe it maintains a wave-like structure for a little bit longer, and then a secondary feature comes in out of the northwesterly flow, strong vortex structure upper front. They don't all wrap up. And if it stays linear, I was thinking, if that feature stays linear, it's going to be really hard to produce the double whammy snow in Minneapolis. Okay, so let's watch this and watch this. Oh. This is really looking good. That's a strong upper front. We won't spend time with the cross-section today because I got other things I want to show you, but strong upper front here. Tropopause is subsiding into the middle troposphere. There's a lot of upper vorticity, but it's in a strip. It's not turning into something isotropic. But that's common at this point in the development. Look at what happens here. Nothing. This is just a shear line. That whole wave has gone away completely. It's been shredded by this confluence zone, just stretched into a linear structure, and it's gone. It had a little bit of impact on the weather. I'm not saying it had no impact, but it's not going to be a cyclogenetic entity. There's no way this thing produces a cyclone. And then I'm hoping this thing, on Tuesday afternoon when I'm looking at the forecast, I'm hoping this thing will wrap up over the Four Corners area, turn into a fairly sizable circular disturbance, and then parade across the upper Midwest and drive substantial PVA by the thermal wind, big cyclogenesis, and heavy snow. Watch what happens to it. So that thing's completely gone by Wednesday night in the forecast, and then this thing stays linear. By God, it will not wrap up. Even out here, it doesn't wrap up over Nebraska. It goes right across the state with no wrap up. And I'll say, at 500 millibars, this forecast was accurate. This is what it looked like. Why in the world were any of us falling for a 20-inch snowfall in Minneapolis? This is just a frontogenetic line. It's got no cyclogenetic potency at all, and the consequence of that is you can't wrap up an occluded structure, which will give you the double whammy snow. Just can't happen. And so, keep on going, and there it goes across the state. It's linear, it's linear, it's linear. Everything's linear in this map. Here's the disturbance from today. So, let me just show you a couple of PowerPoint slides. I can't drone on here, but I'm really excited about this because I think there's some interesting problems that are lurking here. Here is, I'll even do this to make it look a little more efficient. Watch this. I got a slide advance. So here's the final precipitation through 12Z yesterday, so it's not actually final. And a couple of the heavy rainfall, 3.41 inches near Lincoln, or near Springfield, I mean. And then here's the heavy snow across Minnesota and Wisconsin, but this yellow is really about 8 inches of snow. So between 6 and 12, something like that. About half of what was expected. But the distribution looks exactly like those forecasts, doesn't it? There's right at the border, there's a real minimum in the precipitation total. It rained heavily in Chicago, snowed lightly in Janesville, a little bit heavier to the north, and right across there, nothing. The only thing that's not quite right so far is that I think there was more snow in southern Michigan, and that came during the day on Thursday, so it's not in this map. Now, here's what I'm thinking. This is an old storm, but I'm just using it as an example. In a typical extratropical cyclone, there's two broad regions of the cloud mass. One of them is the cloud head, that you can call a disturbance has a cloud head. There's a lot of precipitation that falls out of that. And the other is the frontal band. Sometimes the cold front, you might have an extension here of a warm front. But the geometries are very different between these two places in the storm. Okay? So are there different flavors of vertical motion that operate in the cyclone life cycle? I think there are. And one of the things that I often show is my Q-vector convergence, not my Q-vector convergence, my QG omega maps, but underlying that is using the Q-vector to do the diagnosis of the omega equation, where Q is this interesting feature. This doesn't prompt very much interest, but this part does. It represents the rate of change following the geostrophic flow of the vector del theta, so that the Q-vector tells you how the geostrophic flow is either rotating that vector or changing its magnitude, both of which can produce vertical motion, okay? Because twice the divergence of the Q-vector gives you the omega equation. So watch this. What if you have an arbitrary Q-vector and you split it into a piece that's along the isotropes and a piece that's across them? And here's the gradient del theta. Well, this piece here is the only one that can change the length of that. And this piece right here will change the direction of that. And you can relate those two pieces to the one that changes the length, Qn, is frontogenesis. The one that changes the direction, as it turns out, is PVA by the thermal wind. That's pretty awesome, right? So that you can have transverse couplets of vertical motion that are forced by convergence of the Qn piece of the front of the Q vector, in this case on the warm side. This corresponds to the geostrophic wind intensifying the gradient del theta, so it's horizontally frontogenetic. The response is warm air rises, cold air sinks. Or you can have a long isentrope component of the Q vector converging here and diverging here. This isn't any warmer than here. So there's no transverse or a thermally direct circulation here. It's just a couplet of vertical motions. Ascent where the QS piece of Q converges, and descent where it diverges. And that's related, I won't show here, but that's related to PVA by the thermal wind. But look what it does. if this is the Q vector that leads to ascent where it converges and descent where it sinks, it's going to disturb the orientation of those of those isotropes. They're going to look like this. You're going to start to form cold trough and a thermal ridge where there's ascent. And that's the cyclogenesis issue. That's what you need to have cyclogenesis, to have a storm develop. Not just have precipitation, but to have a cyclone develop. You need this part of the Q vector. And since it's related to PVA by the thermal wind, in the absence of a strong upper vortex, you don't get this. And there's no development. And so that's just an extra way of thinking about it. You can think of this from the PV point of view as well, the same thermal structure. This is a warm anomaly, this is a cold anomaly. That's where you're going to have your development if an upper wave comes along. It makes perfect sense. The transverse couplets, they don't do anything to the baroclinic zone. Look at this. Here's the Q vectors that are cutting across isotropes so that there's descent on the cold side, ascent on the warm side, frontogenesis. And they're going to spin up little vortices in the descent and ascent, but all they do is have flow along the isotropes. There's no distortion of the isotropes in that. So if it starts out linear, a linear band of isotropes, subjected just to this forcing, you'll get vertical motions, but you'll never get the development of a warm or a cold anomaly. So you can't get cyclogenesis. So only one of the two types of vertical motions can drive the cyclogenesis. And here's an example from that storm, 2004. So here's the sea level pressure in 900 to 500 thickness analysis, and here's geopotential in blue at 500 temperature and geostrophic vorticity in green. So there's our cyclone. It's kind of down shear of this feature at upper levels. The vorticity gets a little stronger, so does the cyclone. Then really strong, 984, really intense, and concentrated vortex structure, not strongly linear, right? And if you take a look at the vertical motions, here's the total 700 millibar geostrophic vertical motion from the first time, descent and ascent. Split it into the part that's transverse, frontal based, and the part that's related to the along isotrope Q vector convergence. You need to have this ascent to build that cyclone. It's not doing anything in the frontal region. Here's the total ascent driving the cyclogenesis, descent behind it. Look at how it splits up. This is the transverse part. This is the shearwise part, the part that's forced by the along isotrope Q vector convergence. That drives the cyclogenesis. And you can only get it if you have a strong upper vortex. And there wasn't one in that case. Last thing I want to say, sorry I'm going so long. How do you relate this to the development of occlusions? Well, here's a big snow band from January 1995. Here's what the sea level pressure map looks like. The snow, I'll show you the snow band again. From Door County all the way down to Tulsa. So it's like here. And here's the sea level pressure, really weak, 1,003, 998. Different orientation, but I've kept the same map. And then it gets down to like 1,000 and breaks up. You'd say nothing about this cyclone. This would never attract your attention, except that it snowed like crazy to its north and west. How come? Was it just frontogenetic activity, like this last storm? No. Look at that structure at 700 millibars. Here's the band again where the snow was, right? That's deep occluded structure. That's 700 millibars at 0Z on the 20th of January at the end of this storm. Look at that thermal ridge wrapping back around there. And along this cross section, that's what it looks like. That's a warm occluded thermal structure. And all the heavy precipitation's occurring right in here. And that's what it looks like on a theta E surface. So you have to have that would be a neutrally tilted wave. That's a slightly negatively tilted wave. In order to get this structure, in order to get those dynamics at play in driving your snow. If you don't have a neutrally or negatively tilted wave, this is my contention, you can't get major snow. And so I think there's some truth to that. I don't know how much. Look at what happens at 9 kilometers. This is the PV evolving at 6-hour intervals in that storm. Starts out, maybe you could argue it's positively tilted. Then it gets a little less positively tilted. Then it's about neutral, and it's got this big appendage at low latitudes. And that's where the heavy snow starts to fall, right downstream of this, because that's where the cyclogenesis, as limited as it was in this case, begins to develop. This structure gets more and more developed. Looks like a big treble clef in the music school, right? So that's it for that. And what I'm thinking now is that Posh and I are looking at how to objectively identify occluded structures. And we found a way to do this. And one of the things that's lurking in the future in the research is the GISS climate model makes too many warm occluded structures compared to the reanalysis. How is it doing them? We don't know the answer. What presents itself as a possibility is too many neutrally or negatively tilted waves. And that says something about the broad general circulation in the model that is not right, that does not correspond to what's going on in the reanalysis data. So, and this storm this week alerted me to the fact that you need to have these structures to get 20 inches of snow in Minneapolis. You're not going to get it from frontogenesis only. Linear bands of forcing don't do it. And so there was no cyclone in this storm because there was no upper wave and there was no occluded structure to throw extra synoptic scale forcing on top of what you got from the frontal structure. And so there's something there that's really, I think, a broad science question. So that's what I have. Patrick.
Perfect. Do you mind if I close that?
No, that's fine. Do you want me to help you?
Sure, yeah. If you wouldn't mind going to first the AOS page. So that'll actually fit almost very nicely with what I'm going to talk about for the forecast, which is a development over our region from the cyclone over the west coast that fits exactly with the wrap-up we were just talking about. So if we could go back to weather, please. And then weather watch links and forecast. And we'll go to this new Python version. And let's pull it. So this will be a loop of the surface with 3-hour precip, sea level pressure, and thickness. And we can stop this. And we'll go back to the start. Perfect. And let's go ahead to, okay. So this is a, let's go 2 clicks. So we're at the current time. Perfect. So this is a look model GFS of what's happening right now. Here's our cyclone over the west coast. And very low thicknesses associated with that cyclone. Over our region, we have a high pressure, broad northerly flow, although weak due to the weak pressure gradient. That's typical with high pressure systems. But we'll watch this cyclone as it tracks over the west coast and wraps up and forms a cyclone that's going to be pretty impactful for our region here. So if we could just, we'll just click forward.
Just tell me.
Go. Perfect. Let's stop there. So this is tomorrow at the exact same time. We have our cyclone almost in the exact same position as it was. So this is going to pump a lot of moisture into California, a lot of heavy snows. And as it sits over the west coast, Los Angeles set a low temperature record for yesterday, a bone-chilling 41 degrees. Ooh. So our prayers go out to Los Angeles.
Trust me, they're probably dying.
I'm sure. But as this moves over our region, unfortunately, if you see, we're beginning to form a thermal ridge in the lee of the Rockies. And I'll talk about why as we look at a different level of the atmosphere. But watch this thermal ridge. Let's click ahead a couple clicks. So we see it beginning to form and become more defined. We'll keep going. Let's go to 18Z. On Sunday. So this is Sunday after at noon, and now we have a well-defined thermal ridge right in the lee of the Rockies, right where you expect it as this cyclone tracks over California, Arizona, and New Mexico. We stay in the influence of high pressure, so Sunday is actually going to shape up to be a very sunny and relatively warm. We'll probably get to 41 degrees on Sunday, so we'll enjoy that. But then we'll watch, if we can keep clicking, watch this low develop in the lee of the Rockies. And now we're at 9, I think this is 986. We keep going, or 976, I'm sorry. Now we have, perfect, so this is 12Z on Monday. Now we have a 977 low sitting right over Iowa. And this is associated with a large precipitation band centered right over our region. Because we had that thermal ridge, unfortunately, this is looking like all rain for our region. And all rain for much of the Midwest. If you see the 540 line is well to the north of where all this precipitation is falling. So we have frozen ground, heavy snows up, just snowpack in general, but they also got snow in northern Wisconsin and northern Minnesota. And if you click, let's go like 2 more. We see this precipitation region just move right over us, right over up into Canada. And so when you have a large precipitation region over frozen ground, snow, potential flooding for a lot of this region, and we'll look into QPFs also associated with this storm, the precipitation forecast. But so let's go back a click, we'll look at the same evolution at 500. So if we could go to the 500 loop, please, and we'll stop it again. Perfect. So here's our cyclone, very well wrapped up. A lot of positive vorticity associated with it, and we'll click forward again. And we'll see, so let's go to 18C. Perfect. So now we see purely zonal flow right over the Rockies. So with this, you're going to have adiabatic compression. That's going to warm all of the air sitting right in the lee of the Rockies, and we'll see this in the 850 temperatures. But this is ultimately what makes this system that moves over us a rain event, and not looking like any snow for our region. Maybe there's some snow in the back end of it over northern Minnesota, northern Wisconsin, but largely rain over much of this region. So let's click ahead now. We can watch this wrap up very nicely, and we'll go to once it's over past the Rockies, and we'll stop here. Let's go back to actually. So this is late night on Sunday. You can see a very strong and short, but strong shortwave formed. So we had that ball of vorticity over the west coast. As it moves over the Rockies, as you have column stretching, you can see maxed out vorticity values. So this is very strong vorticity, and it's being advected straight over Nebraska, Iowa, Wisconsin. The thickness field almost mirrored the same 500 hectopascal height field. So this is strong PVA by the thermal wind right over the region where we expect and where we saw a pretty substantial storm form. And if we keep going, we'll see this holds its structure, this very tight shortwave right as it moves over. And once this begins to form, this wrap up, we lose a lot of that advection out ahead of it. If we keep going, we'll see this, what was a potent shortwave kind of just dies out. And same thing with the storm.
Yeah,
You
it's
can
true.
see it becomes messy. But it fits exactly with the PowerPoint that John was showing earlier, where you have strong development when that's a strong shortwave. You have differential vorticity advection. Once you get a wrap up, you have a ball vorticity, you lose that, and you no longer have strong forcing for your system.
And the other thing that's interesting here is that this wave has maybe got a neutral tilt about that time.
Yes.
But it does have a big ridge downstream. So maybe it's not just the tilt of the wave, but what's downstream of it. If you have a ridge down there, you can wrap things up underneath the ridge.
That's right.
In the lower troposphere. But you can't do if the flow is just strong and deformative straight across downstream of your puny little wave. This is not a puny wave. This is a fairly substantial one.
So maybe we owe that thermal ridge that's going to make rain. We owe maybe force this ridge and the heights as well. So maybe that's possibly why it's so strong.
Yeah, the other thing that catches my eye is watch the development south of Hudson Bay. It starts out as sort of a innocuous little vorticity feature there. That thing develops into something pretty substantial. So there's a decent upper frontogenesis going all along that. And I don't know if that has anything to do with the ridginess that's back to the west of that. But the ridginess is important for the development of this, for the development that ensues with this wave over Kansas at this time. It's very true.
Yes, that's very well noted. And then if we could go back a couple clicks too, I'll highlight.
What time?
Let's keep going back to where it's sitting over. So the reason this whole system gets ejected towards our region is you can notice there's another wave incoming. And this is Arctic air, again being pulled from Russia and Alaska straight down the west coast. You can see once this starts to interact and get close to this upper level low, we can keep clicking, we see it gets ejected, and now we have another wave over the west coast and another potential storm maker, another cold temperatures, almost exactly what's happening now.
Yeah.
And this feature looks a lot like what has happened on Thursdays over our region, but now it's on Monday and it's rain.
And it's a little bit better of a wave. The one on Thursday that we were looking at from the Tuesday forecast really is nothing as strong as this in terms of its upper vortex structure and the isolation of the vortex structure and all that.
That's right.
Yeah, very different.
So let's look at the same feature now at 850. We'll go back a tab and do the same loop. And you'll see what I'm talking about with the thermal ridge, most notably here. So just stop it, go back. So here's our low temperatures at 850, cold over the northern half of the United States. Here's our warmth over the southeast. If we can click forward here, we'll watch. Here's this thermal ridge that develops in the lee of the Rockies. And you can see it's perfectly timed if you keep going, I think like 2 more clicks. we develop with the daytime heating this very strong thermal ridge, strong, warm 850 temperatures, and then here's where the low moves over the Rockies, and if you click forward, you'll see the development of a low at 850. And it just pulls all that warm air up towards our region. We stay well above freezing at 850, so very unlikely that we see even mixed precipitation, mostly rain, even all the way up. The zero line is this light blue, so all the way up to northern Minnesota is where you see temperatures potentially at 850 to support snow. So and it almost takes on, if you go back real quick, like a warm, one more click forward. The little warm bubble, 850, that might just be resolution, but, so it is going to be all rain for our region, for this system. And let's see, what else do I want to, oh, let's go to, if we could click, open a new tab. And I wanted to point out, if we could go to weather.gov. I wanted to look at the forecast for, let's go to the Los Angeles area. So this is the forecast for the snow. Yeah, that'll work. You can see there's very heavy snows being predicted. The National Weather Service Los Angeles issued its first blizzard warning in 34 years.
Wow.
So that's how anomalous this event is. There was last night one mountain predicted to get over 100 inches of snow in 24 hours. That would have broken the all-time snowfall record for 24 hours anywhere in the world. However, now it's looking like 80 inches. So a mere 80 inches of snow in 24 hours for one of these mountains just north of Los Angeles.
I think Silver Lake, Colorado has a U.S. record, 96 in 24 hours or
That's right,
something
yeah.
like that.
So close, that's, yeah, close to Big Bear Mountain, yeah.
Yep, yep. It's, yeah, something like right there. And then if we could go to, we'll go to one more website.
That'd be a good place to be right now.
And I'll type this one in. I want to pull up, the low over our region might potentially set records for sea level. Bear with me as I type this. Perfect. So this is a website that tracks the low and high pressure records over the United States, and it breaks it up for month and then also all time. So if we go to February, the record low pressure, it's a very cool website. I recommend going to it. Hopefully this pulls up.
Patrick, if you send that to me, I can add it to the Weather Watch page.
Perfect. Maybe let's try, we just try, oh, there we go. And let's zoom in over like our region. I think if you just click, oh, that'll work too. So if you see we had 977 predicted, these are in tenths of hectopascal, so this is 981.9 hectopascal. If that low moves over Iowa, we're setting pressure records in this region. If it holds its strength, we might even set a pressure record over Madison. So that's how anomalous that this storm is for our region for February. Unfortunately, it falls apart, so it can't, most likely will not set low pressure records over, Michigan, but there's a chance that this could be a record-setting storm in California and also in our region. And that was tied to what I talked about last week, where this set also low pressure records and low temperature records over Seattle.
And this will confuse the national press, because I read something today that's actually talking about the feature in California and heavy snow being part of a huge system that's already plagued the northern states. They're not the same storm.
No.
They're not being clear about that. They're calling the wrong people.
Right. So that's all I had. Are there any questions?
I can't believe you guys didn't look at that bomb in the North Atlantic, that beast.
Just too much right now.
Yeah.
You're right. That's an amazing event.
It's amazing to have John in a room in a storm like that, and that doesn't get mentioned.
I had another agenda today.
That's all right.
All right. Thanks very much, Patrick. Thank you, Pete. We'll see you all next week.
I was gonna say, I missed that storm in California.